Math 2414, Sequences, Video 2, Arithmetic and Geometric Sequences. If you were thinking the word was arithmetic, you're not wrong, but arithmetic is a noun, arithmetic is an adjective. We're going to talk about sequences in general, but there are two very specific types of sequences that show up so often that it's important to be able to recognize them and work with them almost instantly. So let's start with what an arithmetic sequence is. Come on, there we go. All right. An arithmetic sequence is a sequence in which the difference in consecutive terms is constant. In other words, if we refer to the terms generically, then the term prior to the nth term would be the n minus first term. So if you take one term and subtract the term prior to it, you get the same answer every single time. So for example, let's take a look at an arithmetic sequence that we've already seen in the previous video. 1, 4, 7, 10, 13, 16, and so on. We call it a +3 sequence, which is really a loosey-goosey way to describe it, but the correct technical term is this sequence is arithmetic. The difference in consecutive terms is constant. If we did 4 minus 1, we get 3, 7 minus 4 is 3, 10 minus 7 is 3, and so on all the way down. So if you have an arithmetic sequence, there's a real easy way to define the sequence explicitly. In other words, coming up with a function that says, give me the position number and I'll tell you what number goes in there. In this case, a function that says, I don't know, give me the number 4 and I'll turn it into the number 10 because 10 is in the 4th position, et cetera, et cetera. But how do you find the explicit function, the explicit definition of an arithmetic sequence? I thought about just giving it to you, but you should know me by now. I never like to take the straightforward, here's the answer approach. So let's see if we can figure out a way to represent an arithmetic sequence generically and use that representation to come up with this function. So if we wanted to represent an arithmetic sequence generically, we have to first start with some number. So let's call the first term, well, we'll call it A1. Now, if we're in an arithmetic sequence, basically we add something to get from one number to the next. Let's call the number that we add D, and the letter D is for difference. Because if you recall, in the definition of an arithmetic sequence, it's the difference in consecutive terms that's the same. So you can think of it as a plus D pattern. So how would I get to the next term? By adding D to the first term. And how would I get to the second term? By adding D to the, I'm on the second term. How would I get to the third term? By adding D to the second term. So if we add another D, we get A1 plus 2D. And then A1 plus 3D. We'll do one more. A1 plus 4D. So you can almost think of it as how many differences do I have to add to get from the beginning to whatever. Now, here's the trick I want to show you, because what I'm about to show you can be applied to many sequences, not just pretty ones like arithmetic sequences. One trick to massaging the function out of a sequence is to try to expose the pattern 1, 2, 3, 4, 5 within the terms of the sequence. Now, we kind of have that here if you look a little bit closely. I'm going to go to the second term and squeeze a 1 in front of the D. That's how many D's we added to get from the first term to the second term. And if you'll notice, we almost have the pattern 1, 2, 3, 4. They're forced. There's 1, there's 2, there's 3, there's 4. And almost as important, actually as important, everything else is the same. A1, D. Actually, I don't want to underline the plus signs. I'm sorry, I'm getting drawing. Getting draw happy. Erase, please. So let's draw that a little better. Go back in red. Just underline the 1. All right, so as I was saying, if you'll notice in all of these expressions, the A1, the plus, and the D are the same. So in blue, I'm underlining the parts that are the same in each term. And in red, I'm underlining the part that's different. Make this one better here. Now, why am I doing this? Because when you want to come up with a formula, an explicit function for a sequence, one trick to doing it is to identify what's common in all the terms and locate the pattern 1, 2, 3, 4. Now we've located that pattern. The only problem is it doesn't start in the first term. So I'm going to take this first term and rewrite it so that it looks like the others. So in other words, if we were to continue this pattern backwards, we start with an A1, we have a plus, we have a D, but what number would go in front of it? Well, just reverse the pattern that's above it. Going backwards, 4, 3, 2, 1, 0. So if we replace the first term with A1 plus 0D, we haven't added any of those D's yet, we're just at A1, then I don't think I can move that up there. Let me see if I can. Actually, I know I can. I'll just move up here. No, don't do that. Move the whole thing. There we go. Oh, that's so beautiful. All right. So if we replace A1 with A1 plus 0D, look at the nice pattern we have. All 5 terms that we see are identical except where there's 0, 1, 2, 3, and 4. Now, we could start it at 0, but I want to start this at 1 because most sequences will start at 1. And you can always make it start at 1, and here's how. I'm going to do one more thing because I want the underlined parts that are changing to start with the number 1 instead of starting with the number 0. Now, how can we do that? Well, we can do that, if I can get this to draw, by rewriting the 0 as 1 minus 1, rewriting the 1, they're underlined in red, as 2 minus 1, rewriting the 2 right there, double underline in red, as 3 minus 1. And then in the next one, rewriting the 3 as 4 minus 1. That's not a comma there. And then, of course, we could rewrite the 4 as 5 minus 1, but I'm kind of running out of room here. So let's take a look at what we have, what is the same and what is different. I'm going to do the same thing as before. Double underline everything that matches exactly. In fact, everything matches except, let's do this. Let's underline the numbers, the pattern that we try to expose, starting with 1. 1, 2, 3, 4. Everything else is identical. The A1 plus at the beginning and the parentheses, the minus 1 close parentheses, and D at the end. By rewriting each term so that they are identical except for the numbers 1, 2, 3, and 4, we basically exposed the function. All we have to do to write this generically is to say AN equals everything that's the same stays the same. And everything is the same except where there's the number 1, 2, 3, and 4. Where the number 1, 2, 3, and 4 is, that becomes the N. Now, I could have just told you this is the formula for coming up with the explicit representation of an arithmetic sequence, but that's no fun. But I will type it here. All right. If I can get this to cooperate. All right, so if an arithmetic sequence, one starts with an S, has a first term of A1 and a common difference of D, then the nth term is AN, that in parentheses, A1 plus n minus 1 times the difference. I would know this because we will run across arithmetic sequences quite frequently, and it's just so nice to be able to write the nth term explicitly instead of saying add something to the previous term. So let's take a look at a real quick example of an arithmetic sequence and see, or a couple, and let's see if we can crank out their explicit representations. All right, so for this first one, let's start with 10, and we're going to subtract 7 all the way down. So minus 7 is 3, minus 7 is negative 4, minus 7 is negative 11, minus 7 is negative 18. So we'll do one more down here. We'll do, how about 1/2? I meant to start with 1/4. 1/4. Come on, draw. Draw. 1/4, 3/4, 5/4, 7/4. And let's see if we can come up with the explicit representation of both of these sequences. We need the common difference for each one. And remember, the common difference is what you add to get from one term to the next, or excuse me, equivalently, it's the difference in consecutive terms. So if we did 3 minus 10, we would get negative 7. That's what we're adding to each term. So our common difference is negative 7. Our first term is 10. Therefore, the nth term is the first term, 10, plus n minus 1 times the common difference. Now I'm going to put the common difference in front. I know in the formula it was written on the tail end right here. That was just a consequence of how we built the formula, but it's going to get distributed, and it just looks more natural to distribute it from the front. Additionally, pun intended, I suppose, adding a negative could be written more succinctly as minus. If we distribute the negative 7, we'll get negative 7n, and then we'll get 10 plus 7, which is 17. So there's our pattern. I'm going to show you one more trick for finding this final answer real fast in an arithmetic sequence. But let's do the next one, where our common difference is, and if you're not sure, just subtract consecutive terms. 3/4 minus 1/4, that's 2/4, better known as 1/2. And of course, the first term, 1/4. Therefore, our nth term will be the first term, 1/4, plus the common difference, 1/2, times n minus 1. If we distribute the 1/2, we'll get 1/2 n. Then we'll get 1/4 minus 1/2, which is negative 1/4. All right, I'm going to share a dirty trick with you because I like you to know the theory. I like for you to know the method behind the madness, but I also want to show you ways to get through some of these answers quickly. The trick to coming up with this, the final answer, not the answer that you build with the parentheses, but the final answer, is to know two things. What's the common difference? Well, that's pretty obvious. It was negative 7. The common difference is like the slope. But as far as the number that shows up at the end, here's a dirty little trick. The number that shows up at the end is the number that you would get if you push the pattern backwards one space. So for example, on the top one, going from left to right, we're subtracting 7. If we go backwards, we add 7. 10 plus 7 is 17. On the bottom pattern, going left to right, we're adding 1/2. So going backwards is subtracting 1/2. 1/4 minus 1/2 is negative 1/4. If you think about it, that's why, if you think about how we set it up here, it makes perfect sense. We're going backwards one step. But that's a real quick way to get any arithmetic sequences explicit representation. So just to show you how easy it is, I give you a number like 11 and another number like 30, and then we're adding by 19, so 49. Then to get the explicit representation, you start with what you're adding by, your slope, if you will, your common difference, which is 19. And then what follows that is what you would get if you go backwards one. Going left to right is adding 19. Going right to left is subtracting 19. 11 minus 19 is negative 8. So shortcut, And right here, it's about to be highlighted in yellow, explicit formula. All right, so that's for an arithmetic sequence. But you'll notice we also talked about geometric sequences. Or at least I mentioned them. So what's a geometric sequence? Well, an arithmetic sequence is when the difference in consecutive terms is constant. A geometric sequence is a sequence where the ratio of consecutive terms is constant. This is also called a multiplicative sequence. For example, come on, draw. For example, let's say we take 5 and then 15. Now, if this were an arithmetic sequence, you would be thinking adding, in which case the next term would be 25. But as a geometric sequence, it's the ratio of consecutive terms. And I just realized I misspelled consecutive. Doesn't surprise me. In a geometric sequence, it's the ratio of consecutive terms. So if I told you this was a geometric sequence, because right now there's not enough evidence to draw that conclusion, but if I told you it's a geometric sequence, then the ratio, abbreviated R, would be one term divided by the previous term, which is 3. So it's like our multiplier. So if we're multiplying by 3, 15 times 3 is 45. 45 times 3 is 135. 135 times 3 is 405, yes, etc. Now, if you're looking at a sequence and you're not sure if it's geometric, then you compare ratios of consecutive terms. So, for example, if I gave you this, let's say I give you, I don't know, 19. Let's not make it 19. Let's make it 32. And then 128. Then 512, and then 2048, and asked you, is this a geometric sequence? Then you would simply take ratios of consecutive terms. 128 divided by 32 is exactly 4. 512 divided by 128 is exactly 4. 2048 divided by 512 is exactly 4. So the evidence here suggests it's a geometric sequence with a common ratio of 4. All right, so I want to do one more thing with geometric sequences, and that is to come up with the explicit representation like we did here, where we came up with the formula that says, tell me any number in the sequence based on the position in the sequence, that's the n, the first term, and the common difference. I'm not going to invent the wheel on this one. I challenge you, however, to try to replicate what I did when we developed the explicit formula for an arithmetic sequence. I'll just go ahead and tell you what it is for a geometric sequence. Unfortunately, when I film these Zoom videos, there's not a timer to let me know how long I've gone. Sorry if it's a long video. All right, I'm going to be consistent with the wording here. And that wording is an arithmetic, okay, here we go. Okay, the geometric sequence, let's start it. If a geometric sequence has a first term of, we're still going to call it A1, and a common ratio of R, then the nth term is given by, and I'm going to draw this. The nth term is given by, it's your first term, that's a 1, not an I. It's the first term times the ratio to the n minus 1 power. And we'll highlight that because I feel like it's worthy of highlighting. And if you really compare this to the one for geometric sequences, because you know I love to push those theoretical boundaries. If you compare this to the explicit representation of an arithmetic sequence, which was A1 plus D times n minus 1, the formulas are very similar. The A1's in the same place, the R replaces the D, and the n minus 1 is in the same place. but all of the operations, with the exception of the minus, get bumped up one on the order of operations. You know, please excuse my dear Aunt Sally. The addition gets promoted to multiplication right there, and the multiplication right here gets promoted to exponentiation. It's not a coincidence, but by the way, exponents and multiplication are defined, but I just wanted to point that out because if you know one, you really know both. So yeah, okay. So keep in mind that if we identify an arithmetic sequence or a geometric sequence, then we have the tools to quickly come up with the explicit representation, provided we know the first term and the common difference if it's an arithmetic sequence and the common ratio if it's a geometric sequence. All right, and I think that's going to be the end of this video.